Hey everybody, welcome back to Organic Chemistry. Now we're going to go over the syn addition. At this point, you're probably feeling a little bit overwhelmed. You learned about the anti-syn reactions, you learned about the anti-reactions. I want to remind you that you have to think about the big picture, okay? It's really not that bad if you think about that there's really just three categories of reactions. There are syn and anti-additions, there are anti, and there are syn additions. Now, every one of them has common ground. All anti-additions make a triangle as an intermediate. It blocks a side. All of the reactions that do syn and anti, they all make carbocation or a radical, right, with the H-bond peroxide. And what we're going to learn in this video is that the ones that do syn-only addition, they all have things adding at the exact same time. So that's the common trend. I've also been exposing you to stereochemistry. I've been showing you when to use it, when to draw it, and when you don't have to, right? So if there is no stereochem, you don't have to worry. If there is chirality or if there is a cis-trans potential, like in ring systems, a cis and trans, then you have to show stereochemistry, okay? So you'll get the hang of it. Once you get past the next three videos, you're going to have almost the entire chapter. So we're going to go over this chapter now, syn, and then we're going to talk about some other things related to stereochem, and then we're going to talk about a little bit more advanced problems or reaction types, and that really wraps up this whole alkene stuff. We're not going to be done. There'll be two more videos after that, but this is like the heart of this chapter, okay? So hopefully you've had a chance to kind of think through things, you know, take your time with this. Don't force yourself through everything very quickly, and you'll be okay. Just kind of move through it at a reasonable pace. Give yourself at least 4 days to learn this chapter. Okay, 4 solid days of studying, and you'll find you're doing well. All right, let's get started. So in this one, there's only 4 reactions and then a bunch of problems that we'll do. And again, this is a syn reaction, right? So let me write this down now. All syn reactions are concerted, meaning everything adds at the same time. So that's the common theme amongst what we're going to learn now. Now I want you to recognize also that, well actually let's just get started and we'll go from there. So the first one here is called hydroboration oxidation. Now let's say for example we have an alkene, and we were to treat this alkene with well, let me just tell you the goal. The goal here is to make an alcohol. And as you probably can imagine right now at this point, you've learned a few different ways of making alcohols, right? Acid catalyzed hydration, oxymercuration, and now a new one right here. So we'll see why we learn the 3 in just a moment. But let's just go through this one. So if we treat this with hydroboration, boron, BH3, hydrogen borate. So what we're going to have here is the BH3 that's going to add onto this alkene. Now you have to remember that this is concerted. So this BH3 is going to drop right on top of the alkene. And the way it works is, if you can imagine, I'll draw it over here. If we have, let's say, a BH2 and an H, one of those of the BH3, one of the H's, is going to extend out and it's going to drop down onto this alkene. So at the same time, so the alkene's going to make a bond to one of them, and the other one makes a bond to the alkene carbon. Now, the thing is that because this happens at the same time, and you recognize that this here is bigger, right? This is a larger side, and this is a smaller side. It turns out that the larger side is going to drop into the lower degree location, the less sterically hindered. So when this comes in, imagine if, let's say, we have a whole bunch of branching here, right? And so when this boron comes over, it's going to drop down so that it attaches to the lower degree. If it tried to come in here, the boron, it would be repelling with all that branching that's going on. So the first step is where the BH2 goes onto the low degree and the H goes onto the high degree. So here's, let's see over here, there's a primary and a secondary, right? So let me just delete this. So we have a primary and a secondary. The BH2 adds on here, and the H adds there. This is a syn addition, meaning the two things going onto the alkene are adding on the exact same side. It lands right down on top of it, or from below, right? So you could have drawn it like that, Ba2 and H as well. They can come in from below or they can come in from above. Now, why do we do this? Well, what we actually did is we created a marker or a placeholder. Let's say you wanted to put an OH on the low degree carbon. Well, you can't do that with oxymercuration or acid catalyzed hydration. You wouldn't be able to do that because in both cases the OH goes to the high degree. So here's a reaction that allows us to put a boron in, and the reason why we did that, by the way, is BH2. The reason why we did that is because we're going to now be able to replace it with an OH. And that's what happens next. So from here, if I write H2O2, OH minus. Now, there is a mechanism for this, but I don't bother learning it yet. If you want to study it, you can look at it from your book, Chapter 8, the Alkene chapter. But I just want to tell you, first know what happens, because the mechanism is long-winded. But it's really like such a unique mechanism that they don't ask you questions on it ever. So I just want you to understand, books teach it to you, teachers teach it to you, but just first get the idea down. What happens here is the boron is going to be replaced with an OH. How it happens, we don't care right now. And so the end result is that we get an OH on the end. So we made a primary alcohol. And that's it. This is what the reaction does. So if you want to get a primary alcohol, this is the way to go. Okay, now let me give you a comparison. And by the way, the BH3 is usually in THF. So tetrahydrofuran, if you happen to see that, that's just a solution, right? This is the solution. And THF tends to be a good solution for this particular reaction, okay? So don't get confused if you happen to see THF, or any ether, by the way. THF is an ether. So if you see an ether, it's just a solution. Now, what's really important is the hydrogen peroxide and hydroxide, because that's what allows us to get rid of the BH2 and put in an OH. Okay. Now, imagine as an example, let's try to achieve the following goal. Let's say we have that right there, and our goal is to get that right there, or that right there, or that right there. These are three different alcohols, and in all three cases my goal is to figure out what's the best reagent to start with, and this will show you the difference between these these different reactions that we're describing. So in all three cases we have a different location for the alcohol. In the first one, I want to put an OH here on the red carbon, right? But now what I know to myself is that this is secondary, but this is quaternary. And if I'm not careful, if I make a carbocation, I'm going to have a rearrangement, right? So this is the perfect scenario for why we would use oxymercuration, because oxymercuration will guarantee us that we won't have a methyl or a hydride shift. So the OH goes exactly where you want it, on the high degree alkene carbon. And that's it. It won't go anywhere else. Okay? So this is perfect for oxymercuration. HgOAC2 in water, and then step 2. This is step 1. Step 2 is NaBH4. So the key here, there's no rearrangement. And that's why oxymercuration is used. Okay? So a lot of times, if the neighbors were in higher degree, then you could use oxymercuration or acid catalyzed hydration. Either one will do the same thing. Interconverting one from the other, it wouldn't matter. The only time it matters is if you have rearrangement potential and you don't want to have that rearrangement, right? So that's an example here. Now in this case, the red carbon is here and we had a methyl shift. So we're having one of these methyls jump over. So how do you do that? Well, if you make a carbocation on that secondary carbon over here, right? Then we can have a methyl shift because the next door neighbor is a higher degree. So this is perfect for acid catalyzed hydration. So use H plus, H2O, and you will get the OH on the high degree after rearrangement. See that? So this has rearrangement. And that's why we would use this reaction over the oxymercuration. Okay? That's the only time you use one over the other for those two. And now in this last example,